Hola, ¿qué tal a todos? Bienvenidos de nuevo al seminario de álgebra. Hoy tenemos el privilegio de que nos va a presentar Tullio Ceccherini-Silberstein y su plática va a ser First Order Model Theory, Surjunctive Groups, and Kaplansky Stable Finiteness Conjecture. Thank you very much, Tullio, for accepting this talk. We're very happy that you are talking to us today in our seminar. And please go ahead. Thank you.
Thank you, Alonso, for the invitation. I'm very happy to be, virtually in Guadalajara, a place which I enjoyed very much visiting. That was before COVID, I guess. So I would like to give this talk, which puts together concepts from geometric group theory, symbolic dynamics, and ring theory. And the link, the main ingredient comes from first order model theory, so from logic. Okay. So if you have questions, please interrupt me, and I will be glad to try to answer to your questions. Okay. So this is a joint work with Michel Coornaert from Strasbourg and Kien Phung from Montreal. So let's start with the definition, which leads to Kaplansky direct finiteness and stable finiteness conjecture. So for me, a ring is always, it's an associative ring, which is unital, which means that it has an identity element, which I denote by 1R. And let me define first direct finiteness. So a ring is said to be direct finiteness if, with this formula, I say that left inverse is also a right inverse. So one-sided inverse are automatically two-sided inverses. Okay, so this is a very natural definition. And we have a strengthening of this definition, which is given by stable finiteness. So you require that for every dimension D, the D by D matrices with coefficients in your ring R is directly finite. So this means that if you take a square matrix A with coefficients in R and another square matrix B with coefficients with R with the same dimension, when you take the product, if the results is the identity matrix, then also in the other order you get the identity matrix. Okay, so clearly, as I said, stable finiteness is a strengthening because the matrices, the one by one matrices over a ring clearly coincide with the ring itself. It is very simple to prove that finite rings are stably finite, that all abelian rings, this is clear, so in particular fields are stably finite. And then you have this very familiar from linear algebra, that if you have a vector space over a field K, then the endomorphism ring of the vector space V, so all the linear maps from V to V, is stable finite if and only if the dimension of your vector space is finite. What is remarkable is that the two definitions, direct finiteness and stable finiteness, indeed are not the same. Indeed, you can find in the book by Lam, Lam is a famous ring theorist, rings and modules, this is the title of the book, then there is a construction of a ring which is direct finite but is not stable finite. Now, let's define or recall what are group rings. Suppose you are given a group G and a field K, then you can consider this set K power G is just the set of all maps from G to K, no structure at all for the moment. So given such a map alpha, so an element of this K power G, we define the support of alpha as the set of elements in the group G such that the value, the corresponding value, does not vanish. So it's different from zero, the zero element of the field K. Okay. Then with the notation K bracket G, we define the set of all maps alpha whose support is finite. And this set is easily seen is a vector space. Well, indeed, K power G is also a vector space. So K bracket G is a subspace of K power G. But in addition, you can define the product. So if you take such map alpha and beta, you can make the product of them. So it is a map which is defined as follows. If you take an element G in the group, then the value is given by this product. So you multiply alpha H1 and beta H2 over all elements H1, H2 in G, whose product is G. Note that this sum is indeed finite. Why? Because only finitely many H1 survive, since alpha has finite support, and the same holds for beta. You can also write the same expression as in the second line expressed. This product is called the convolution product of the elements alpha and beta. And this way, K bracket G becomes an algebra, which is called the group ring, or more generally, the group algebra of G with coefficients in K. Now, Irving Kaplansky, he was a very famous algebraist. He proved that if you have any group G and any field of characteristic 0, for example, the complex numbers, the real numbers, the rationals, and of course there are many other fields of characteristic 0, then if you perform the construction of the group ring, then the corresponding group ring is stably finite. But he could prove it only in characteristic 0, and he raised the question whether the result also holds in characteristic P, so in finite characteristic. So putting together the problem and the theorem, we can formulate the problem as a conjecture that for any group G and K any fields, so regardless of the characteristic, the corresponding group ring is stably finite. So now I turn a moment to the notion of a notion from geometric group theory, and I want to define you the notion of a Sophic group. So let's first start with some notation. If X is any finite set, we denote by sim of X the symmetric group of X. So this is the group of all permutations of X. Then this sim X, which is clearly a finite set because X is finite, we can equip it with the distance called the Hamming distance, which is which is defined as follows. So if you take two permutations, sigma 1 and sigma 2 of the set X, their distance, this is rather called the normalized Hamming distance. It measures, then it counts the element of the set X at which the two permutations differ. Okay? Differ means that sigma 1 of X is different from sigma 2 of X. So you count this number of elements at which the two permutations differ, and you normalize by dividing by the size of X. So clearly, if sigma 1 and sigma 2 are the same, the set of the numerators where you take the cardinality is empty, so it is 0, and which you expect. The distance of two identical elements is 0. Okay? Okay, this defines the Hamming distance, and now we have the definition of sophicity, a concept going back to Gromov and to Benji Weiss, which is as follows. So we say that the group G is Sophic if, given any epsilon, so arbitrarily small epsilon, and an finite subset of G, so arbitrarily large subset of G, you can find a non-empty finite set X and the map, just the map from the group G into this finite group, the symmetric group of X, satisfying the following two conditions. So you see, the first condition means that phi is almost a homomorphism, when restricted to elements in F. So what it means almost? So you see F phi of G1, G2, phi of G1, and phi of G2 are permutations. And you can compose permutations. So here, phi G1, phi G2 is the composition of these two permutations. And so you have a permutation on the left and permutation on the right. And the Hamming distance tells you how close are these permutations. So to say that it is an almost homomorphism means that the corresponding permutation phi of G1, G2 and the product phi of G1 times phi of G2 is small, and the small is in terms of the epsilon, which you fix in advance, in the Hamming distance. Now, if we impose only the first condition, you could set phi of G to be the the trivial permutation. So you want to avoid such a triviality. And so you also require that if you have two distinct elements, G1 and G2 of your finite set F, then the Hamming distance between the corresponding permutation phi of G1 and phi of G2 is close to 1. So 1 minus the distance is greater or equal than 1 minus epsilon. Okay, so this is to avoid trivialities. So here I made a list of examples of Sophic groups. In the following slides, I will give you a hint. So finite groups are Sophic. More generally, residually finite groups are Sophic and amenable groups are Sophic. And it is remarkable that up to now, there is no example of a non-Sophic group. So we don't know if non-Sophic groups exist. It is most likely that such non-Sophic group indeed do exist. So why did I introduce you to Sophic groups? Because there is a remarkable result due to Gabor Elek and André Szabó, which tells you that the Kaplansky stable finite conjecture holds true for Sophic groups. In other words, if you have a Sophic group G, you have any field K, so in particular also of finite characteristic, then the corresponding group ring is stably finite. So as I promised, I want to give you a hint why such classes of group are Sophic. So why finite groups are Sophic? So if you take a finite group G, then you can consider the so-called Cayley Cayley homomorphism, which maps every element G into the permutation of the group G itself, given by just by length multiplication. Okay, so phi of G applied to the element H is the new element in the group G8. This is indeed a homomorphism. This is used in the famous theorem, which is referred to as Cayley's theorem, which tells you that any group is indeed a subgroup of a symmetric group, a sort of characterization of groups as subgroups of symmetric groups. And here I also remarked that the second condition also is trivially satisfied because you have, in this case, right cancellative. Every group is cancellative, so you can simplify. Okay, what are residually finite groups? Residual finiteness is a generalization of finiteness. It asks the following, that if you have a non-trivial element in your group G, then you can detect non-triviality by looking at suitable finite quotients of the group. So given any non-trivial element G in the group, you can find a finite group K and the group homomorphism phi from G into K, such that the image of G under your homomorphism phi is different from the trivial element of the group K. Okay? Then it is easy to see that you have this other reformulation of residual finiteness, namely that for every finite group G, for every finite subset of G, there exists finite. Now, before you ask just for one single non-trivial element. Now I take any finite subset G, then there exists a finite group K and a group homomorphism as before, such that now you require that the restriction of phi to this finite set F is injective. So using this characterization of residual finiteness, you then define, you check that it is sophic, just as a generalization of the finite groups with the Cayley theorem. But now you apply as follows. So phi of G to K. I remind you that K now is the quotient. K, just by making the phi of G now is an element in K, and you take the multiplication by K. So it's a combination of the homomorphism given by this characterization and the Cayley theorem applied to group K. And again, here I show you that condition star and condition double star are satisfied. You don't need any epsilon, and you don't need to take any for any epsilon you have that it is a homomorphism. So it is very strongly satisfied, the both condition star and double star, regardless of epsilon. But you have to fix your finite subset F. Now, in this slide and the next one, I prepared the proof that amenable groups are sophic. So here, let me remind you what is an amenable group. So there are several equivalent definitions, and I take this definition here, that for every epsilon prime and every finite subset S of G, then you can find a finite subset X of G, which is, as we say, almost invariant by all elements in S. So what it means invariant? So if you have X, which is a subset of G, you can multiply each single element in X by G, by the group element G, and you have another subset. Here I have a picture. You have X is like a rectangle in here, and Gx is this shifted, you multiply on the left by G, okay? So you require that this difference of the elements in X which do not belong to Gx is small than in proportion. So less or equal than epsilon prime times the cardinality of X. So this is almost invariant, but almost given by epsilon prime by all elements in S. So, for example, here I draw a little picture with Z, with the integers. So if you take a long interval and G and you take as say 1, 2, 3, for example, then when you shift, you see the part X is this part here, Gx is this other part here. When you take S and you remove Gx, is this small quantity here, which in proportion to the whole of X is very small. So this epsilon prime corresponds to this length compared to the one of X. Okay. Okay. Here I made the detailed proof that amenable group is sophic. So we fix now epsilon, arbitrarily small, F, finite subset of G, arbitrarily large. You construct with set S, which is you add the trivial element, the identity element of the group to F, and you take also the inverses of F, and then you square it. It means you take all possible products of elements here. You define epsilon prime to be epsilon divided by the cardinality of this set S, and you apply the definition that I gave you for amenability. So you have A, the implication with this, you apply this definition here, so that you have such a condition. Then you define X sub epsilon as the intersection of all translates of X, of your finite set X, which you find there, by elements in S. Okay? So what is remarkable is that such element X epsilon is contained in X. In particular, X epsilon itself, because S belong the identity elements belongs to S. So in particular, X epsilon is contained in X, and because of the property of the definition, you can check that X epsilon is large inside X. So okay, you need some calculations to do that, but you trust me, it is large within X. And now this X sub epsilon will be the set where everything works perfectly. I have just to make now a little aside observation, because we want to define the action on all of G. So I have fixed X, and I remark the following. The size of X is the same as the size of Gx. You translate a set, it has the same size, okay? So if you remove Gx from X, or you remove X from Gx, you obtain two sets which have the same cardinality. So here you have this part here, which would be the first one, and this shaded part, which is the other one in the other subsets. So you can always find a bijection from the two of them. So here I indicate if this is little x, this will be the image under alpha of sub G of this bijection. Okay, then I define for every group element G and every x in capital X, the following action. Phi of G of X is equal to Gx if Gx already belongs to X. Otherwise, Gx comes out of X, so you are in this shaded part, and you apply alpha G, so which brings it back to X. Okay, so you can check that this indeed yields a permutation, and if X belongs to X epsilon, you can check that phi of G1, G2 applied to X is the same thing as phi of G1, phi of G2 applied to X. So it behaves well, like a homomorphism for the element in X sub X epsilon. And again, also the cancellation property holds for such elements. And since the set X epsilon is large, because of this condition, when you apply the Hamming distance, you see that it satisfies the conditions. Okay, so this is a proof that amenable groups are indeed sophic. Now let's turn to symbolic dynamics, because I have to define surjunctivity. So let G be a group, let A be a set. A priori, we don't ask to be finite, which is called just the alphabet. And you form this power set, A power G, which is just a set of all maps, which are called configurations, from G to A. So you should think that A is a set of colors, and X is a coloring of G. So you color each element of G with the elements, with the colors in A. Okay, so mathematically, this you can write it also as the product of copies of A indexed by the elements of G. Okay, we equip it with, okay, let's just write, if you are not familiar with uniform structure, it's with the so-called prodiscrete topology, which means that in this product space, you equip this finite set A with the discrete topology, so it is compact. So if you take the product, it is compact by Tikhonov topology. Okay. Then you not only you equip it with the topology, but also with an action of the group, which is called the G shift. So if you have such a configuration X and a group element G, I define the new configuration Gx as follows. Its value at the input element H of the group G is just the value of the configuration X at the group element G inverse H. Okay? You can check that the G shift is a continuous action when you equip the configuration space with the pro-discrete topology. And now we are ready to give the definition of a cellular automaton. So a cellular automaton is a self-map, so it's a map of the configuration space into itself, satisfying the following local properties. So there exists a finite subset S of G, which we call the memory of the cellular automaton, and the map mu from A power S. So A power S now is a set of patterns which support S. So all the maps from S to A. So mu is a map from A power S to A. This is called the local defining map associated with the memory set S, such that you have the following expression for the cellular automaton. So if you take a configuration X, the new configuration tau of X, so the image of X under the cellular automaton tau, evaluated at G, so this is an element of A, is a color, is made as follows. You take the configuration X, you shift by the G shift via the element G inverse. So G is the same as here, G inverse. So this is the new configuration. You restrict to S, and so you produce an element in A power S, and then you apply mu. You get an element in A. Okay, so this defines you a cellular automaton. There is the famous Curtis-Hedlund-Lindon theorem, which characterizes cellular automata. So again, maps from A power G to A power G satisfying these local conditions are exactly the continuous, uniformly continuous if A is not finite, but let's restrict to A finite. So to the continuous map, which are also G equivariant. G equivariant means that they commute with the shift. In other words, if you start with the configuration X, you shift by G and you apply the cellular automaton tau, this is the same thing as firstly applying the cellular automaton and then shifting by G. So we have defined cellular automaton. So here I give you an example. G is the group of integers. A, the alphabet, is the cyclic group of order 2. So it's 0, 1. I want to have it a group structure on it. And S, the subset of the group G, is just the subset -1, 0, and 1. And mu, the local defining map, is just sum. So since the group G is the integers, you can regard any configurations as an infinite string of zeros and ones. The way I have defined, as you see, is like cells, one next to the other. So this is the motivation for cellular automata. Okay, you have in this, the first cell, you have here, you have 1, again 1, in this cell is 0, or if you prefer the color of the cell is 1, 0, and so on. Now, at n is the element of the group, G is the integer, so it's an element n, and I want to know what is the value of the configuration tau of X at element n. So what I have to do, you see, the S is the memory, it's like a window. I am only allowed to look at this pattern here, 1, 0, 1. And the local defining map mu tells me that I have to sum the values. So I have 1 plus 0 plus 1 is 0 in our set A. It's modulo 2. Okay? So you get 0. If you take the next value in n plus 1, you should look the values at n plus 1, and n plus 2. Now you have 0 plus 1 plus 0 is 1, and so on. So you update your configuration X according to this rule, and you get the new configuration tau of X. Okay? So now we are in a position to give the definition of a surjunctive group. G is said to be surjunctive if for any finite alphabet A, every injective cellular automaton, so from A power G to A power G is a cellular automaton, which is injective, then it is necessarily surjective. Okay? You see, this condition is reminiscent to some, in some category, we have such implication. For example, in the category of finite sets, every injective self-map is automatically surjective, and of course also vice versa. In the category of vector spaces, if you have a linear endomorphism, you know that if the vector space is finite dimensional, then every injective such linear map is also surjective. Indeed, also the reverse holds. It does not hold if the vector space is infinite dimensional. And more generally, if you have an algebraic variety over an algebraically closed field, every injective morphism, which in the category of algebraic varieties, is automatically surjective. This is the famous Ax-Grothendieck theorem. Okay, now Gottschalk conjectures that all groups are surjunctive. Let me list here classes of groups for which it is known that conjecture is true. So all finite groups. This is trivial, as I said, because A, the alphabet is finite, G is finite, means that the configuration space is finite. And so in every injective map of the configuration space into itself, regardless it is a cellular automaton or not, it is automatically surjective. The fact that residually finite groups are surjunctive, this is a result due to Lawton, and the fact that amenable groups are subjunctive can be seen as a consequence of the so-called Garden of Eden theorem. I will not mention it anymore here, or simply by the use of the entropy. This will be presented in the next slide. And more generally, because Sophie groups, as we have seen, generalize both notion of residual finiteness and amenability, this is a very deep result going back to Gromov and Weiss. Let me remark you that as for Sophie groups, we don't know if there exists non-surjunctive group. Okay, so in the following slide, I give you a hint of why residually finite group are surjunctive. Okay, so suppose you are given a configuration X and the subgroup of G. We say that X is H periodic. I repeat, H is the subgroup G. If such a subgroup fixes fixes X, so all elements in the subgroup fixes X. This is the shift, the G shift, but you just ask for the elements in H. More generally, we say that X is periodic if its stabilizer, so the set of group elements which fix X, is finite. Okay, this is the same thing as saying that, sorry. If its orbit is finite, so this is equivalent to say that its stabilizer is of finite index in the group G. Okay, sorry, I repeat. A configuration is periodic if its orbit under the action of the whole group G is finite, is a finite set of configurations. This is equivalent to say that the stabilizer, so the group elements which fix X, is of finite index in the group G. So we denote by P of AG as the set of all periodic configurations. So it's the same thing as saying the union of all H periodic configuration where H runs over all finite index subgroups of G. Now, it is a fact that if tau is a cellular automaton, so A is any finite any finite alphabet, and you take X to be a configuration which is H periodic, then when you apply the cellular automaton, tau F, this is also H periodic. This follows from G equivariance of the group. Remember, the equivariance means that it commutes with the shift. So if you have, since H of X is equal to X for every group element in this subgroup H, then tau of H of tau X is the same thing as tau of Hx, which is tau X. So this means that tau X is fixed by H. Okay? Note that the set of periodic configurations, H periodic configuration, is a finite set. In fact, its cardinality is given by the power of the size of the finite set A, of the set of colors, with the power of the index of the group, of the subgroup H in G. So now, because of the observation before, we have that tau maps periodic configuration into periodic configuration. But because of the first observation, if tau is injective, it maps H periodic into H periodic. But since the H periodic is a finite set, and tau is injective, it must send H periodic configuration onto H periodic configuration. So the image of periodic configuration equals the set of all periodic configurations. So if tau is injective, this is indeed an equality. Now it can be shown by using residual finiteness, that the definition of residual finiteness, that this is equivalent that the set of periodic configuration is dense in the A power G, in the set of all configurations. For example, if G is Z, the integers, which is residually finite, then it is easy to see why the periodic configurations are dense. So now let's conclude the argument. If you look at the image of the whole configuration space by tau, it contains the image of all periodic configurations. But we remark that if tau is injective, then this equals the all periodic configurations. But tau is continuous, and A power G is compact, so the image is compact, and therefore closed, because it is also Hausdorff. And therefore, since it contains a dense subset, it must coincide with the whole edge. So we conclude that the tau is surjective. Okay, for amenable groups, the easy argument is by using entropy. So amenable, if G is amenable, one of the characterization is about the existence of Fellner nets. So is exactly the previous definition, just that, but you have, instead of fixing the subset S, you ask that for every G, you have this asymptotic invariance. So Fi is a family, F is a family of finite sets, non-empty sets, which are asymptotically invariant in this sense. Okay, now given a subset X of A power G and F a finite subset of G, we denote by X sub F as the set of all restrictions of the configuration in X to this finite set F. So it's a set of patterns. Of course, it's a finite set. It's a subset of the patterns with support F and alphabet A. So we define for a subset X the entropy with respect to this Fellner net F as the lim sup. You take the logarithm of this of the cardinality of this finite set. You normalize by the cardinality of the Fellner Fi, and you take the lim sup. This is called the entropy. Now, if X in particularly is a subshift, which means that it is closed in the pro-discrete topology and G invariant, so invariant under the shift, then a deep result by Ornstein and Weiss tells you that this definition does not depend on F of the Fellner set F, and additional, you can drop the sup, so it's a genuine limit. Okay, you can prove that the entropy of the full shift, so of the whole configuration space, is nothing but the logarithm of the cardinality of the alphabet A. You have this monotone property, and the following invariant property for cellular automata. So if you have a cellular automaton X, you compute the entropy of the image tau of X, then it cannot increase. So it's less or equal than the entropy of X. So by using this property here and the previous one, which tells you that you have a proper subset, a proper subshift of the full shift, then the corresponding entropy is strictly smaller than the entropy of the full shift. Okay, so combining these two things, you have that if tau is injective, then the image on the one hand should have the same entropy, and therefore cannot be this inequality cannot be strict. Okay, and this gives you that amenable groups are surjunctive. So now Kien Phung proved the Kaplansky conjecture for surjunctive groups. In other words, the group ring, the group algebra of the group G with coefficients in any field K is stably finite. So somehow Phung's result, together with the Gromov-Weiss theorem, which proved every Sophie group is surjunctive, somehow factorizes the result by Elek and Szabo, which tells you that every Sophie group satisfies the Kaplansky triple finiteness conjecture. So now I need a little lemma and generalize the notion of cellular automaton for linear cellular automaton. This is why at the beginning I started with the alphabet, not necessarily a finite set. So now our alphabet is a vector space over the field K, and you perform the same construction, V power G as a set of all maps from G to V. This is a vector space over K, and you have the definition of a cellular automaton, but now we want linear cellular automaton. So we just ask that this map, not besides satisfying the local property defining cellular automaton, is also K-linear, so it respects the vector space structure. In terms of the local defining map, this is the same as saying that mu is K-linear. And it can be shown that the space of linear cellular automata is a K algebra. So if the dimension of the vector space V is finite, so let's call it D, then this K algebra is isomorphic to the algebra of D by D matrices with coefficients in the group ring. So here we have the, you may understand now why we use cellular automata, what is the link between cellular automata and group rings. So linear cellular automata over with the alphabet, a vector space of finite dimension D is isomorphic with this ring of D by D matrices with the coefficients in the group ring. Okay, so okay, maybe I skip this part here, and now I start the to explain you what is the link making everything work properly. So model theory of algebraic closed field. Now, it would be too difficult to give a very complete exposition of model theory, but I just try to give you some ideas. The language of rings, of first order language, is the following. You have two binary functions, plus and minus, and multiplication. So here x stands for multiplication. These are binary function symbols, and then you have some so-called constant symbols. 0 represents the 0 element, and 1 represents the identity, the unit of the ring. Okay, so you can build some formulas in this language. For example, how do you express associativity? You ask that for every x, for every y, and for every z, you have that x plus y plus z is equal to x plus y plus z. So this is the associativity property for the sum. How do you express that every element in a ring is invertible? For every x which is non-zero, there exists an element y such that xy is equal to 1. Okay, so it means that the ring admits a right inverse. This is another formula. There exists an element x such that x squared is equal to y, where y is equal to negative pi. Okay, so for example, this formula holds in the complex numbers. Okay, there exists an element whose square root which is the square root of the number negative pi, but it does not hold in R, for example. So in this case, y is called a free variable. What is a sentence? A sentence is a formula with no free variables. So the first two are free. There are no free variables, so these are sentences. Okay. Now, what is elementary equivalence for fields? We say the two fields K1 and K2 are elementarily equivalent, and we write with this symbol if they satisfy the same first order sentences, so formulas with no free variables, in the language of rings. Okay, for example, if you have two fields which are isomorphic, then they are equivalent. Now, you have two important principles due to Lefschetz, Solomon Lefschetz. So you have that two, it's very important, algebraically closed. This is very important. Algebraically closed fields of the same characteristic, they are elementarily equivalent. So for example, as we mentioned before, if they are isomorphic, they are also algebraically equivalent, but not vice versa. For example, the algebraic closure of Q is of characteristic 0, so its algebraically closure is also of characteristic 0, is equivalent by Lefschetz principle to the complex numbers. But clearly, these are not isomorphic because the algebraic closure of Q is countable, whereas C is clearly uncountable. Okay? What is very important also is this second principle, which tells you the following. Let phi be a first order sentence in the language of fields, of rings. The following conditions are equivalent. This sentence phi is true in some algebraically closed field of characteristic 0. Then, as we can remark that by Lefschetz principle 1, this is the same as requiring that it is true in all algebraically closed fields of characteristic 0. And this is the bridge between characteristic 0 and positive characteristics. There exists a natural number n such that phi is true in all algebraically closed fields of characteristic larger than n. So the second one can be rephrased, but say the phi is true in all sufficiently large characteristic algebraically closed fields in such a characteristic. Okay, so this left principle 2 is the, as I said, will be established the bridge between zero characteristic, where we know that essentially that the Kaplansky conjecture hold, to the other case. Okay, now what you see, we want to apply this principle to a first order sentence over the language of rings. So here is the lemma. If we have a group G, D, this will be the dimension of the D by D matrices. Now, matrices over the group ring. Group ring, they recall these are elements with finite support in K power G. So these are maps from G to K with finite support. So let S be a finite subset G which supports all entries of such matrices. Okay, so this is what we fix. Then there exists a sentence which I call psi sub D and S, because it depends just on D and S. Of course, also the group, but the group G is fixed in the language of rings, such that a field K satisfies this condition exactly if there exist two matrices A and B of dimension D with coefficients in the corresponding group ring, such that the support of the two matrices is contained in this finite set S, and we have on the one hand that the product AB is equal to the identity matrix, but on the other hand BA is not equal to the identity matrix. So it's a failure of the condition on the Kaplansky stable finiteness conjecture. Okay, so here is just the logic, the formal expression, which is in red. Now I'm afraid I won't have time to read it in detail, but this is just to say why I can express this condition here in a first order sentence in the language of rings. So now I'm in a position to give you the proof that if G is surjunctive, then the group ring in K with coefficients in K is stable finite. Case 1, K is finite. Now, if G is surjunctive, we have that G is K surjunctive. So what means K surjunctive? That every linear cellular automaton with coefficients in K is, which is injective, is automatically surjunctive. This was the part which I skipped, which gives you, it comes from the isomorphism of the linear cellular automata and in this case with the group ring. Okay, so this is very easy to handle. So if the group is finite, if the field is finite, everything is handleable. Now consider the case where now K is the algebraic closure of the field with P elements. P is the prime is a characteristic of the field of P elements. Okay. Now consider now alpha denotes the Frobenius automorphism, which raises at the P power every element in the field. Now we denote by Kn the subfield which corresponds to the fixed point under the nth power of the Frobenius automorphism. So it's a subfield, and it has P to the power n elements. And you have that Kn is a subfield of Km whenever n divides m. So now, if I define L sub n as the field of fixed points under the n factorial power of the Frobenius automorphism, then it becomes an increasing sequence of subfields, and you have their union is equal to the whole of K. So now, if I have two matrices n b with coefficients in Kn, whose product in AB is equal to the identity element, now the coefficients are in K, but since there are only finite many entries, and the union of all this Ln is the whole of K, then there exists a sufficiently large N0 so that these two matrices A and B do indeed belong to the matrices with the coefficients in such Ln0 ring, group ring. Okay, but now this is a finite ring. We apply the first case. We have AB is equal to the trivial with the identity matrix, and so also in the other order must be the identity matrix. Now, if K is algebraically closed of characteristic P, then we use Lefschetz principle 1. This algebraically closed field K is equivalent to the algebraic closure of Fp. But we have already handled the case of the algebraic closure of Fp, and the result holds true. So this covers case 3. Now, suppose that K is algebraically closed of characteristic 0. Then we use Lefschetz principle 2, which tells you that if it was not true in characteristic 0, then it would have a failure of the of our theorem, of our result in characteristic P. But we have already seen that in characteristic P, for algebraically closed fields of characteristic P, it is covered by case 3. We will have a contradiction. So this must hold also for algebraically closed fields of characteristic 0. So now this is the general case. Let K be any field. If K is any field, consider its algebraic closure, L. Then, if it is a field of characteristic 0, you apply case 4. If the field is finite, you apply case 3. So the group ring with coefficient in L, I repeat, L is the algebraic closure of K, is stable finite. But then the K in the group ring with coefficient in K is contained here. So all coefficients here will be particular coefficients here. So the result, the statement holds trivially. So this this subring is stable finite as well. So this ends the proof and ends, if you want my talk. I have just some final remarks. So there is a theorem by Ken Dykema and Kate Yushchenko that if you have a group G and a field K, then the group ring K with coefficient in G is stably finite if and only if the group ring of the direct product of G with any finite group F is directly finite. So please, here I have stably finite, here is direct finite. So as a corollary, to ask for Kaplansky's stable finite conjecture, or if the analog apparently weaker condition of direct finite conjecture, is exactly the same thing. Here I have some final remarks about other famous Kaplansky conjecture on group rings. But you have to ask that the group you are thinking of is torsion-free. So there are no elements whose non-trivial elements whose power, so G to the n, equal to the identity. So a torsion-free group. K is any field. So we have the so-called Kaplansky unit conjecture, which asks that the group ring with coefficients in K has no non-trivial units. A unit is an invertible element, and non-trivial means different from the elements of G, which clearly embed here. This is a stronger condition than Kaplansky idempotent conjecture. So the group ring does not contain trivial idempotence. Elements M such that M square is equal to M. Oh, wait. let me say that the unit conjecture has been recently disproved by Giles Garden with the group, the famous Promislov group, and the field with two elements. The idempotent conjecture infers the Kaplansky zero divisor conjecture, so which asks that the group ring has no zero divisor. Zero divisor are elements, non-zero elements whose product gives zero. And the weakest condition is indeed this stable finite, direct finite conjecture, which, as we remarked, are equivalent. So this, what I want to say, that you have this famous conjecture, and they all are related by these implications. So analogous arguments using model theory applies to this Kaplansky unit idempotent zero conjecture, in the sense that if you have a result in characteristic zero, then you have it in all characteristic, because you can express the existence of non-trivial units, the existence of non-trivial idempotents, or the existence of zero divisors in terms of first order model theory. Okay, so this is the end of my talk, and I thank you very much for your attention. I'm ready to answer for your possible questions.
Thank you very much, Tullio.
Thank you for your attention.
So, si tienen alguna pregunta en inglés o en español.
A ver, Aloncito, una pregunta.
Sí.
¿La estabilidad finita tiene que ver con la estabilidad finita tiene que ver con encontrar ciertas cotas? Pregunta.
Okay, so the question of Paz is if you can reformulate maybe, or if it's related, stably finite with
yes.
some bounds. You can reframe it in terms of a bounds.
Yes. Bounds in what sense?
Sí, como que en qué sentido cotas, Paz.
Por ejemplo, o sea, o que si nos puede definir bien lo que es la estabilidad finita en este contexto.
Well, basically, if you can remind the definition of stable finite. Just
of course.
Yeah.
Okay, so stable finiteness, the simple thing is about direct finiteness. Okay, the product of two elements is equal to the identity, means that the product also in the inverse order is equivalent to the unit element of the ring. Stable finiteness means that the ring of D by D matrices is directly finite, so in the above definition, for every dimension D.
Mm-hmm.
Okay.
Yes. I think maybe she was misled by the name stable, because stables give the impression that
the
at some point
question of Maria related about the size of D. So maybe if you can, you see, the example by Lam of a direct finite ring which is not stable finite. Now I don't remember if already taking the 2 by 2 matrices it doesn't work. So is Maria's question related to the size of D?
Sí, que se tiene que ver con el tamaño de D. Yes,
o sea, con la distancia de Hamming, entonces.
No, más bien con el tamaño de D, de que
de
es
la
dimensión de las matrices.
De la dimensión.
¿Sí? Yes, okay. She says that. Yeah, link with D, but it should be for all D, right?
Exactly.
Yeah.
You ask for all D. Of course, for D equal to 1, you have the direct finiteness. But then, of course, you can you could define two direct finite, 3 direct finite, 4 direct finite. Okay, or more generally, D direct finite for every single D. Okay. So stable finite means that it is D directly finite for all D, if you want.
Okay.
I don't know if this was
yes.
And for anyway, for every D, you have the expression in terms of cellular automata with the alphabet vector space of dimension D.
Okay,
So
okay.
you do it in a for every D, you have the parallel with the cellular automata in that dimension.
Okay.
I think your question was related to this point, right?
Yes.
With the dimension of the vector space.
Yes. Thank you.
You're welcome.
Tullio, I have also a couple of questions.
Yes.
To see so one is related with the entropy. So you define in your slides entropy of a subshift, right?
Yes.
But there is also this notion of entropy of a dynamical system, right? Like a topological entropy of a dynamical system. So my question is related with that because, for example, cellular automata, you can also think of them as discrete dynamical systems. And you can ask, for example, what's the topological entropy of a cellular automaton as a dynamical system, not the topological.
It's the same thing.
It's the same. Okay.
When you have the notion of topological entropy of a dynamical system, usually your dynamical system is a compact metrizable space. And you have you use covers separating. You have several definitions which eventually coincide. I can send you, and you can forward to interested people, a version of this in terms of in the case when you have a uniform space. So it's a more general, just a uniform dynamical system. Okay, so they are coincide, and in the case of subshifts is exactly the same thing. Of course, when you say dynamical system, you can ask with the group acting, not just a single transformation.
Okay. Yes.
And of course, the group needs to be amenable. Of course, now there are the notion of Sophic entropy, and then it's even more general. But at the level of your question, it's exactly the same thing. In the case of subshift, is the same thing as the one I have defined.
Okay, so would be
maybe it could be interesting that in the case when you have linear cellular automata, so you have linear subshifts now, okay? So you look at not only which are closed in the pro-discrete uniform structure, so in the corresponding topology, not only they are G invariant, so invariant under the shift, but they are also invariant under the vector space operations, okay? Linear subshift. Then you can define something which is called mean dimension. So instead of counting the elements in X sub F, you count, you look at the dimension of X sub F, okay? And you have very analogous results. This was done in my first paper, actually, on linear cellular automata with Michel Coornaert, where we studied this mean dimension and the action of cellular automata.
Okay.
So there is this counterpart which is related to your question, because is the counterpart that you need in the linear setting.
Thank you. And just one very short question to finish, not to delay you more.
No.
So basically, I was wondering if you think is more open question. If you think there are some hopes of trying to attack to prove the Gottschalk conjecture using techniques from model theory. So perhaps you would need some kind of other type of model theory, right? Not related with the fields, with the language of rings and fields.
Yes.
But you might need, I don't know, some model theory for groups, right? Or for the language of groups. I don't know if there is some hope. Maybe there are not enough tools in model theory to do that.
I understand the point. You see, model theory, this is very helpful to pass from. It is very much used in algebraic geometry.
Okay.
Because you have typically when you do algebraic geometry, you take a field, you don't specify the characteristic. But sometimes you need to move from characteristic 0 to other characteristics, and you have all these tools coming from model theory. Now, I understand your point, but I don't see what would be the key tools. What would, the Lefschetz principle 1 and Lefschetz principle 2, these are the key tools for all such kind of arguments. Also for algebraic varieties, the Axe theorem, you use such tools, okay? And for groups, of course, there is model theory for groups. For example, you may have heard that Zilil Sela, on the one hand, and Olga Harlampovich and Alexei Myashnikov, they proved that all three groups are elementary equivalent. So they satisfy the same
sentences.
Sentences. Thank you. Sentences in the language of groups. So if you can ask, what is the class of groups which are elementary equivalent to the Sophic groups? Maybe it's closed under the class of Sophic groups is closed under elementary equivalence. Now, since we don't know of groups which are non-Sophic, of course, the class of groups which are elementary equivalent to Sophic groups contains the class of groups. Most likely they are the same, because maybe everything can defining sophicity it seems to be somehow expressed in that language. But this is in the spirit of your question, I think. You see?
Yes.
If you cannot really express, you see, you can. So returning to surjunctivity, let me think. Because you see, everything is finite when you define a cellular automaton. Yeah, you fix the alphabet. If you have a counterexample, let's say, a counterexample to Gottschalk conjecture would be a finite alphabet A and the group G. Okay, so A is somehow it's maybe for if you take a surjunctive group G, for such A there would be no problems, but for such, so you have to fix A, and then the way you express the cellular automata, you have mu, no, the local rule. This can be somehow expressed in the definition of mu is well defined. Now, I remember the following problem. I think that surjectivity cannot be, I'm afraid that surjectivity cannot be expressed in terms of first order language.
Okay.
You know why? Because first order cannot deal with subsets somehow. How do you, it seems to be, maybe there exists an element, how do you say that something is not? There exists an element such that for all, maybe yes, I don't know, for all elements in the source, the image is different, right? Maybe it's okay. Now I'm not 100% sure.
Okay.
Because when I was studying first order language, just to become acquainted with the theory, I remember something that it's not expressible, but I'm not 100% sure. But of course, it's your question is interesting because
yeah, would be nice to find that.
Yes.
Okay. Well,
what is the time in Guadalajara?
Now it's 11:15.
11:15. So
yes.
you still have.
Yeah, we're starting the day here. Yes.
Okay. So I thank you all for your attention.
Thank you very much again, Tullio. I will send you the link of the talk, and we'll keep in touch.
Okay, thank you very much.
Thank you very
Chao,
much.
Alonso.
Bye.
Best
Bye.
regards to everyone. Thank
Gracias
you.
a todos por asistir. Muchas gracias. Hasta luego.
Hasta
Gracias.
luego. Hasta luego.
Hasta luego.